The nearest star system looks close in the night sky, but reaching it may be one of the most terrifying challenges humanity has ever imagined. Alpha Centauri is not just far away. It exposes the brutal limits of our rockets, our bodies, our technology, and even our courage. A journey there could take generations, demand impossible choices, and reveal that space is far more hostile than we want to believe. Today, we explore the terrifying reality of traveling to Alpha Centauri. Now, let's begin. 41 trillion kilometers. Not 41 million, not 41 billion, 41 trillion, written out in full. That number has 14 digits and takes up half a line. Most people read it, nod, and move on because the human brain was never built to genuinely feel a number that size. We can recite it, we can type it, but feel it, understand it in our bones the way we understand the distance from the couch to the refrigerator? No. And that gap between knowing and feeling is exactly where our intuition collapses. That is the distance to Alpha Centauri, the closest star system to Earth, our nearest neighbor in a universe of hundreds of billions of galaxies. And if you boarded the fastest spacecraft humanity has ever built right now, tonight you would die on that ship. Your children would die on that ship, and your great-grandchildren would still be drifting somewhere in the dark, not yet at the destination. That is not a metaphor. That is not poetic exaggeration. That is the cold arithmetic of where we are and where that star actually sits. And here is the part that should genuinely unsettle you, that is the closest one. Most people picture Alpha Centauri as a single star, a bright point on a star chart, a destination with a name. The reality is more complicated and, in some ways, more interesting. Alpha Centauri is not one star. It is a system of three. Alpha Centauri A and Alpha Centauri B are two stars locked in a gravitational embrace, orbiting their shared center of mass once every roughly 79 years. They are similar to our Sun in size and temperature. A slightly larger and brighter, B slightly smaller and cooler and from a distance. They appear as a single point of light to the naked eye. Then there is the third member, Proxima Centauri, a small gas and dim red dwarf star sitting much farther from the AB pair, bound to the system by gravity, but physically separated by a vast distance even within the system itself. Three stars, one name, one deceptively calm dot in the southern sky. The distance to this system measured most precisely to Proxima Centauri. The closest of the three is 4.24 light-years. To the A and B pair, it is 4.37 light-years. These numbers are standard in any astronomy textbook, and they carry the quiet authority of established science. 4 light-years. Sounds almost modest, doesn't it? Less than 5. Single digits. That is the trap. 1 light-year is the distance light travels in a single year, moving at 299,792 kilometers every second. Not per hour, per second. 1 light-year comes out to approximately 9.46 trillion kilometers. Multiply that by 4.37, and you land at roughly 41 trillion kilometers, the number we opened with, the one your brain smoothly processed and quietly discarded. Let's try to make it real. Imagine the sun is a basketball. You place it at the center of Times Square in New York City. At that scale, Earth is a small grape sitting about 26 meters away. The moon is a pea, just 6 centimeters from that grape. Mars, at its closest approach, is roughly 40 meters from the basketball. The entire inner solar system fits within a 1-block radius. Now, at that exact same scale, where is Alpha Centauri? It is another basketball, sitting in Los Angeles, 4,400 kilometers away. And between those two basketballs, no air, no light, no heat, no sound, just an absolute perfect crushing void stretching across a distance so immense that even the comparison strains to hold its shape. That is the gap we are talking about crossing. Within this system, the most discussed destination is a planet called Proxima Centauri b. Astronomers confirmed its existence in 2016 using the European Southern Observatory's HARPS spectrograph, detecting the faint gravitational wobble it produces on its host star. It orbits Proxima Centauri within what scientists call the habitable zone, the range of orbital distances where liquid water could theoretically exist on a planet's surface. Not where life definitely exists, not where conditions are comfortable, just where the temperature math doesn't immediately rule out liquid water. That discovery mattered enormously. It meant that the nearest star to our sun hosts a world that is, at minimum, not obviously and immediately impossible for life. That is the most cautious possible excitement, and the scientific community felt it anyway. Because proximity changes everything in theory. 4.24 light-years is still 4.24 light-years, regardless of what sits at the end of it. And light, the fastest thing the laws of physics permit to exist, the ultimate speed limit of the universe, takes 4.24 years to make that trip. Not 4.24 hours, not 4.24 days, 4.24 years. Think about what that means practically. The light hitting your eye right now when you look at that star left its source back in 2020. You are not seeing Alpha Centauri as it is tonight. You are seeing a 4-year-old photograph delivered at the maximum speed reality allows. If something catastrophic happened to that star system last year, a massive flare, a collision, anything you will not know for more than 3 more years. The universe does not do real-time updates. And here is the part that quietly destroys your sense of scale. Light is incomprehensibly fast. It circles Earth 7.5 times in a single second. It crosses the distance from Earth to the Moon in 1.3 seconds. Earth to Sun, 8 minutes and 20 seconds. And even moving at that speed, the ultimate speed, the ceiling of what physics permits, it still takes 4.24 years to reach the nearest star. So now ask yourself the obvious question. How long would it take us? How long would it take a spacecraft, a real one, built from real materials, burning real fuel to cover that distance? Take a guess. 40 years. 100 years. 200. Maybe think again. We will get to the exact number in just a moment, and it is going to reset everything you thought you understood about our place in this galaxy. But first, one small note on the light you saw tonight. That light from Alpha Centauri left its source in 2020, the exact year COVID began. That star system has been quietly radiating away for billions of years, completely unaware that a virus shut down the entire human world for 2 years, that economies collapsed, that people lined up around city blocks for vaccines. By the time any signal from Earth confirming the pandemic is over reaches Alpha Centauri, it will be 2029 at the earliest. That star doesn't know the pandemic ended. And honestly, given what comes next, that might be the least of its concerns about us. 4.24 light-years, 41 trillion kilometers, a number your brain accepted and immediately filed away without truly processing. That is the first trap this journey sets, making the impossible sound like a long commute, a slightly inconvenient drive, something that modern engineering, given enough time and funding, could probably sort out. It cannot. And the reason why is not a matter of ambition or political will or budget allocation. It is a matter of physics. And physics, unlike governments or corporations or dreams, does not negotiate. But if the distance alone is already impossible, then our only weapon, rocket technology, is somehow even more terrifying. Here's why. New Horizons is the fastest spacecraft humanity has ever launched away from Earth. Right now. As you read this, it is still flying somewhere beyond the orbit of Neptune, deeper into interstellar space than any human-made object before it, barreling through the void at approximately 58,000 kilometers per hour. That speed is genuinely extraordinary by any human standard. It would take you from New York to Los Angeles in about 4 minutes. It crosses a distance equivalent to Earth's circumference in under 26 minutes. And at that speed, reaching Alpha Centauri would take approximately 78,000 years. 78,000. Let that land properly, because the number has a context that makes it even more devastating. Homo sapiens, modern humans, our species, us, first appeared on this planet roughly 300,000 years ago. That means if our ancestors had launched a New Horizons-class probe on the day the first anatomically modern human drew breath in East Africa, that probe would currently be less than 1/4 of the way to Alpha Centauri. We would be watching it on instruments 300,000 years into the mission, and the destination would still be more than 50,000 years away. We are not talking about a long trip. We are talking about a timescale that swallows entire civilizations, ice ages, and the complete arc of recorded human history multiple times over before the spacecraft even comes close. The reason comes down to a fundamental constraint that every rocket engineer knows and quietly dreads: the Tsiolkovsky rocket equation. Russian scientist Konstantin Tsiolkovsky derived it in 1897, and in the century plus since, nothing has overturned it. The equation describes a brutal feedback loop at the heart of chemical propulsion. To go faster, you need more fuel, but more fuel means more mass. More mass means you need even more fuel to accelerate that mass, which adds more mass, which requires more fuel. The equation spirals against you every time, and at the velocities required for interstellar travel, the math becomes grotesque. To accelerate a crewed spacecraft to even 1% of the speed of light using chemical rockets, you would need a fuel-to-payload ratio so enormous that the mission becomes physically absurd. The fuel tank would need to be larger than anything we could conceivably construct or lift off the ground. Chemical rockets got us to the moon. They got us to Mars' orbit. They are magnificent machines for the solar system. But the solar system and interstellar space are not the same category of problem. They are not even the same category of scale. Now, Parker's solar probe presents a more interesting case and a more seductive illusion. Launched by NASA in 2018, Parker's solar probe holds the current record as the fastest human-made object ever measured. During its closest solar flybys, it reaches speeds of approximately 692,000 kilometers per hour. That number is almost 12 times faster than New Horizons. If you heard that without context, you might feel genuine hope. Surely something moving that fast could cross interstellar distance in a manageable time? But Parker's solar probe achieves that speed by falling toward the sun, using our star's massive gravitational field as a slingshot. The moment it leaves that gravitational environment and enters the flat, empty expanse of interstellar space, it cannot maintain that velocity. There is nothing to sling it, no gravitational assist, no energy source powerful enough to keep it moving at those speeds without continuous thrust. And continuous thrust requires fuel that simply does not exist in those quantities. Parker Solar Probe's record-breaking speed is a gravitational loan. The universe charges interest in the form of deceleration, and in interstellar space, there is no refinancing available. Even if you could somehow maintain that 692,000 km/h speed across the entire distance, which you cannot, the trip to Alpha Centauri would still take roughly 6,800 years. Still not a human timescale, not even close. SpaceX Starship enters the picture here because it represents the most ambitious leap in rocket engineering in decades. It is a genuinely remarkable vehicle, fully reusable, designed to carry large payloads to the Moon and Mars, capable of being refueled in orbit. Elon Musk has spoken openly about making humanity multiplanetary, beginning with Mars. Mars, at its closest approach to Earth, sits approximately 225 million kilometers away. Starship could potentially make that journey in several months. That is extraordinary. That is a genuine achievement in the history of spaceflight. But consider what it means in context. Alpha Centauri is not just farther than Mars. It is 180,000 times farther than Mars. Not 180,000% farther. 180,000 times. If Mars is the distance from your front door to your mailbox, Alpha Centauri is on the other side of the planet. Mars is the backyard. Alpha Centauri, in terms of practical engineering reality, is not a different destination. It is a different category of existence, as unreachable with current technology as another continent is to a person standing on a beach with a pair of water wings. So how long would it actually take us to get there, with our best available technology pushed to its absolute limit? 78,000 years, give or take. And not a comfortable 78,000 years in some kind of futuristic hibernation pod. 78,000 years of a spacecraft quietly coasting through absolute nothing, its instruments slowly degrading, its fuel long spent, its mission controllers dead and forgotten, and replaced by civilizations that may not even speak the same languages that named the probe. If we had launched New Horizons the day the last woolly mammoths were walking the Earth, it still would not have arrived. So, if conventional rockets are not the answer, surely we have something better waiting in the wings. Some next-generation propulsion concept that changes the equation entirely. Saying we will fly to Alpha Centauri on current rocket technology is a bit like saying Christopher Columbus was going to cross the Atlantic on a bamboo raft. Technically, a raft floats. The direction is correct. The physics of buoyancy are not violated. You simply will never, ever arrive. The method and the mission are so mismatched that calling it a plan is a courtesy. Our rockets are magnificent for what they were built to do. They were built for a solar system. And the solar system, vast as it seems from down here, is a puddle. Alpha Centauri is the ocean. So what machines have scientists actually imagined to replace them? And why does every single solution hide a deadly trap inside it? Nuclear fission was supposed to be the answer. Back in the 1960s, NASA and DARPA jointly funded a project so audacious that it sounds like science fiction even today. Project Orion proposed propelling a spacecraft by detonating a rapid sequence of nuclear bombs directly behind it, using the blast waves to push an enormous shock-absorbing plate, driving the ship forward with each explosion. The theoretical top speed for an Orion-class vessel somewhere between 3 and 5% of the speed of light. At 3% of the speed of light, the journey to Alpha Centauri would take roughly 140 years. At 5%, closer to 85 years. Still longer than a human lifetime, but suddenly in a range where multi-generational missions or long-duration crewed voyages become at least conceivable. The engineering, on paper, was not fantasy. It was ambitious, but grounded in real physics. Then reality arrived in the form of the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space. Project Orion was effectively killed not by science, but by international law. Beyond the legal barrier, the practical problems were severe. The fuel requirements were enormous. The radiation exposure to the crew would be extreme, and no material science at the time, or since, has produced a shock plate capable of surviving thousands of nuclear detonations in sequence over decades of continuous operation. So nuclear fission gives us a direction but not a door. 100 years is still longer than most people live, and the technical and political barriers remain. For now, insurmountable. Antimatter propulsion is the one that makes physicists' eyes light up because the energy density is genuinely extraordinary. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass into pure energy. No combustion, no partial conversion, no exhaust inefficiency, total annihilation, total energy release. In theory, a kilogram of antimatter meeting a kilogram of ordinary matter produces energy equivalent to roughly 43 megatons of TNT. An antimatter drive would be, by an enormous margin, the most energy-efficient propulsion system physically possible. The problem is production. CERN, the most sophisticated particle physics laboratory on Earth, produces antimatter as a byproduct of high-energy particle collisions. After decades of operation and billions of dollars in infrastructure, CERN can produce a few nanograms of antihydrogen per year. A nanogram is 1/1000th of a gram. To propel a crewed interstellar spacecraft to even 10% of the speed of light would require metric tons of antimatter. Not grams, not kilograms, tons. At CERN's current production rate, accumulating enough antimatter for such a mission would take longer than the age of the universe. Even optimistically scaled-up production facilities, running continuously for centuries, would fall catastrophically short. And that is before addressing the storage problem. Antimatter must be contained in magnetic fields with perfect precision, because any contact with ordinary matter triggers immediate annihilation. One containment failure, and the ship ceases to exist. Antimatter sounds impressive in Star Trek. In practice, the gap between what we can produce and what we need is so vast that calling it a challenge is almost comedic. Ion thrusters represent a real technology actually flying on real spacecraft right now, and they are genuinely efficient. Instead of combusting fuel, they ionize a propellant gas, usually xenon, and accelerate the ions electrically to very high exhaust velocities, producing thrust with far better fuel efficiency than chemical rockets. The catch is the force they generate. NASA's Dawn spacecraft, which used ion thrusters to travel to the asteroid Vesta, and then the dwarf planet Ceres in the asteroid belt, produced a maximum thrust of approximately 90 millinewtons. For comparison, that is roughly the force of a sheet of paper resting on your palm. Dawn took years to reach its destinations within our own solar system, accelerating at a glacial pace that would have been imperceptible from inside the spacecraft. Ion thrusters are extraordinary for long-duration missions where fuel efficiency matters more than speed, but for interstellar travel, where you need to achieve a significant fraction of the speed of light, blowing gently on a freight truck is not going to move the needle. The most credible near-term proposal for actually reaching Alpha Centauri comes from Breakthrough Starshot, an initiative announced in 2016 by physicist Stephen Hawking and billionaire Yuri Milner, backed by $100 million in seed funding. The concept is elegant and genuinely exciting. A ground-based laser array of extraordinary power, potentially gigawatts, would focus its beam on an ultra-thin light sail attached to a tiny spacecraft weighing just a few grams. The radiation pressure from the laser would accelerate the sail to approximately 20% of the speed of light. At that velocity, the journey to Alpha Centauri would take roughly 20 years. 20 years. That is a human timescale. That is achievable within a career. That is the first number in this entire conversation that doesn't require the word 1,000 after it. But here is the architecture of the trap hidden inside. The spacecraft weighs a few grams. It carries no life support, no crew, no scientific instruments beyond the most miniaturized sensors imaginable. It arrives at Alpha Centauri moving at 20% of the speed of light with no means of slowing down because there is no braking mechanism, and the laser that accelerated it is now 4.24 light-years behind it. The spacecraft flies through the Alpha Centauri system in a matter of hours, snapping what images it can before disappearing into the darkness beyond. It cannot orbit. It cannot land. It cannot be retrieved. It is in every practical sense, a very fast postcard. Breakthrough Starshot. At its most optimistic, sends a gram-scale probe on a flyby of another star system, sending humans carrying life support, food, water, radiation shielding, communication arrays, landing vehicles. The mass requirements scale by a factor of millions, and suddenly the laser array required to push that mass would need to be larger than anything humanity has ever constructed. Which leaves the Alcubierre warp drive, a concept proposed by Mexican physicist Miguel Alcubierre in 1994 that, fascinatingly, does not technically violate the laws of physics as currently understood. The idea, rather than moving the spacecraft through space, you compress space ahead of the ship and expand it behind, creating a bubble that effectively surfs a wave of space-time. Inside the bubble, the crew experiences nothing unusual. The ship itself never locally exceeds the speed of light. It is the bubble that moves. The problem: the energy required to generate and maintain such a bubble, according to calculations, is equivalent to the mass energy of an object approximately the size of Jupiter. The entire planet Jupiter, converted entirely to energy, and the exotic matter required to achieve negative energy density, the theoretical ingredient that makes the math work, has never been observed to exist in any quantity, anywhere, under any conditions we know how to create. Warp drive is not engineering. It is a mathematical concept waiting for physics we do not yet have. So we arrive at the painful conclusion that no technology, theoretical or actual, proposed or funded, elegant or brutal, can currently place a human being at Alpha Centauri within a single lifetime. Not one. The fastest credible concept sends a grain of rice-sized probe on a one-way flyby. Everything else either breaks the laws of physics, requires energy budgets that beggar all imagination, or takes longer than recorded civilization has existed. Antimatter sounds impressive in Star Trek, but producing enough to actually move a crewed ship to Alpha Centauri would consume the entire economic output of human civilization across several thousand years. Elon Musk could not afford it. Every government on Earth pooling resources could not afford it. The math simply does not care about ambition or net worth. But suppose we accept it. Suppose we decide that a journey lasting generations is the price we pay, that we build a ship and we go, however long it takes. Then the next question becomes something far more disturbing. How do you actually keep human beings alive inside that ship for 100 years with no help coming from anywhere? In space, the human body begins dismantling itself. Not dramatically, not all at once, quietly, systematically, with the patience of a process that has no reason to hurry. Without gravity pulling on bones and muscles, the body interprets the absence of load as permission to stop maintaining mass it no longer needs. Astronauts aboard the International Space Station lose approximately 1 to 2% of their bone density every single month. Not every year, every month. After 6 months on the ISS, returning crew members frequently cannot walk unassisted. Their legs have to relearn what ground feels like. Their cardiovascular systems have redistributed fluid in ways that take weeks to reverse. 6 months. That is the current long-duration benchmark for human spaceflight. A journey to Alpha Centauri at any speed our theoretical engines could achieve would take decades, at minimum, more likely a century or longer. A crew member who boards that ship with a healthy skeleton would, without intervention, arrive at the destination, if they arrived at all with bones so degraded they could not stand on the surface of another world. The entire point of the mission, rendered physically impossible by the journey itself. The only practical engineering solution is a rotating spacecraft. Spin the ship fast enough, and the centrifugal force against the outer hull mimics gravity, keeping fluids distributed, bones loaded, muscles working. It is the same concept Christopher Nolan visualized in Interstellar, the slowly turning ring station. The physics are sound. The engineering is extraordinarily complex and expensive. Maintaining precise rotational stability over a century of operation through vibrations, micro-collisions, mechanical wear, and the thermal expansion and contraction of deep space is a problem that has never been seriously attempted. The ISS does not rotate. No spacecraft ever built has used rotation for artificial gravity over a long duration. We are talking about constructing and operating something we have never built for a time period longer than most nations have maintained stable governments. That is just the gravity problem. The ship has many more. Power is next. Once a spacecraft leaves the inner solar system, sunlight becomes too faint and diffuse to provide meaningful energy through solar panels. By the time you are in interstellar space, the sun is just another star bright, but not close enough to power anything. The only credible long-duration energy source for an interstellar ship is nuclear, a fission reactor, running continuously, without replacement parts, without the ability to shut down for maintenance, without engineers from Earth available to diagnose problems. A nuclear reactor powerful enough to run life support, lighting, agriculture, medical equipment, computing systems, and propulsion for 100 years, with zero external support. No reactor in human history has ever operated under those conditions. The most long-lived operational reactors on Earth have run for decades with constant maintenance crews, regular inspections, and the ability to import components from a global supply chain whenever something wears out. Strip all of that away, and the engineering challenge becomes something altogether different. Food is where the problem turns almost philosophical. Closed-loop agriculture growing food in a fully sealed environment where waste is recycled back into nutrients and nothing is lost sounds like a solvable problem. In 2023, NASA successfully grew lettuce aboard the ISS, a small victory, genuinely useful, and widely celebrated. But the most ambitious closed-loop life support experiment in history remains BIOS-3, conducted by Soviet scientists in 1972. A crew lived inside a sealed ecological system in Siberia, attempting to grow all their own food and recycle all their own waste. The experiment lasted 180 days before the system began losing equilibrium, CO2 levels fluctuating unpredictably, crop yields declining, microbial populations shifting in ways the designers had not anticipated. 180 days, not 180 years. NASA is researching growing lettuce in space, which is genuinely good. But you will need to eat lettuce every day for 36,500 consecutive days. That is a new definition of the phrase, getting tired of salad. Medical care aboard a century-long mission confronts a wall of problems that no amount of clever engineering fully resolves. Appendicitis. For instance, a routine emergency surgery in any terrestrial hospital has never been successfully performed in a zero-gravity environment. The fluid dynamics of surgery change fundamentally without gravity to keep blood and organs where they belong. Blood does not pool downward. Organs float. The instruments behave differently. Techniques developed over generations of ground-based medicine do not transfer cleanly. Now extend that problem across every possible medical emergency a human population might face over 100 years' strokes, heart attacks, cancers, broken bones, childbirth complications, psychiatric crises, infectious disease outbreaks. The ship needs a fully operational hospital. It needs physicians across multiple specialties, and those physicians cannot call for backup or transfer a patient to a higher level of care. Every medical decision is final. Population genetics add another constraint that people rarely consider. A crew of 20 or 30 people, the kind of number that sounds large for a spacecraft, is genetically catastrophic over multiple generations. Inbreeding depression, the accumulation of harmful recessive mutations, the loss of immune diversity. These are not hypothetical risks. They are established population biology. Credible estimates for a minimum viable founding population capable of maintaining genetic health across a multi-generational voyage range from 500 to 1,000 individuals. Some researchers argue for higher numbers. Nobody argues for lower. 1,000 people on a ship for a century. That is not a spacecraft anymore. That is a small city, sealed inside a metal hull, flying through nothing, with no resupply, no evacuation option, and no outside assistance of any kind. And the materials holding that city together. No alloy, no polymer, no composite material currently known to science has been tested for structural integrity under continuous cosmic radiation exposure over 100 to 200 years. We extrapolate from shorter duration data. We run models. We make educated assumptions. But we do not know, cannot yet know, how the hull will behave, how the seals will hold, how the joints will fatigue. After a century in an environment that has no precedent in the history of human engineering, do you think you could live well inside a sealed room for 10 years? Not visit outside occasionally? Not have deliveries arrive? Not have a window that opens just sealed, recycled air, artificial light, and the same walls every day? For 10 years, most people struggle to honestly answer that question. Now multiply it by 10. That is the minimum commitment for anyone aboard an interstellar ship. And unlike a prison sentence, there is no release date. There is only the destination if the ship holds together long enough to reach it. But even solving every single one of these problems, the gravity, the power, the food, the medicine, the population, the materials, the universe has been quietly preparing something else. Something that requires none of our cooperation to deploy and arrives without announcement. But even if you solved all of that, the universe still has one silent weapon waiting, and it can destroy your ship in 1,000th of a second. At 10% of the speed of light, a grain of sand kills your ship. Not damages it, not dents the hull, kills it. A particle of interstellar dust weighing approximately 1 milligram, struck at 10% of the speed of light, delivers kinetic energy roughly equivalent to a tactical nuclear weapon. Not a metaphor, not an approximation for dramatic effect. Pure, verifiable physics kinetic energy scales with the square of velocity, and 10% of the speed of light is approximately 30 million meters per second. The math produces a number that belongs in weapons specifications, not spacecraft engineering manuals. And interstellar space is not empty. That is the critical misconception that feels intuitive but is completely wrong. Between the stars, there are dust grains, ice particles, microscopic rock fragments, and debris distributed at densities that seem negligible until you are traveling at a fraction of the speed of light. At that point, what was effectively nothing becomes a continuous ballistic assault on the leading edge of your spacecraft. Every second of the journey, the ship is running through a field of particles that, at cruising speed, each carry the destructive potential of military ordnance. There is no steering around them. They are invisible at those distances and velocities. By the time any sensor could detect a particle large enough to matter, the ship would have already passed through it. Interstellar space also contains approximately 1 hydrogen atom per cubic centimeter on average. That sounds like nothing, and at normal speeds, it is nothing. At 10% of the speed of light, that sparse hydrogen becomes a continuous stream of high-energy ionizing radiation slamming into the ship's hull and everything inside it. The crew is not simply traveling through space. At that point, they are effectively inside a particle accelerator, bombarded by a constant flux of radiation that no amount of standard shielding fully stops without adding mass so extreme it defeats the entire propulsion system. Current radar and detection systems cannot identify objects smaller than a few meters at ranges sufficient to allow evasive action at interstellar cruise speeds. Reaction time is zero. Not nearly zero, exactly zero. The object and the ship occupy the same space before any response is possible. The engineering requirement is therefore not to detect and avoid it, is to survive the hit. Which brings its own spiral of problems. Two theoretical shielding approaches exist, neither of them adequate on its own. Magnetic shielding can deflect charged particles, protons, ions, electrons by wrapping the ship in a powerful electromagnetic field that bends their trajectories away from the hull. This works reasonably well for the ionized component of interstellar medium. It does nothing for neutral particles, dust grains, ice fragments. Anything electrically uncharged simply passes straight through the magnetic field as if it is not there. Physical shielding, a dense barrier of water, polyethylene, or similar material at the ship's nose, can absorb and scatter incoming particles effectively. But every centimeter of shielding adds mass, and mass is the enemy of every propulsion system ever conceived. Adding enough physical shielding to meaningfully protect against high-velocity particle impacts could double or triple the ship's total mass, requiring dramatically more energy to accelerate, which the engines cannot provide. You need both types of shielding simultaneously, working in combination, covering the entire leading surface of a ship that may be kilometers long. The engineering complexity is staggering. The mass penalty is potentially mission-ending. Cosmic radiation is a separate problem running in parallel with the particle impact threat. Earth's magnetic field, the magnetosphere, deflects the vast majority of cosmic rays and energetic particles before they reach the surface. We live inside a protective bubble so effective that we rarely think about what exists outside it. In interstellar space, that bubble is gone, completely. Cosmic radiation in deep space exposes a crew to radiation levels approximately 700 times higher than the annual safe exposure limit used by NASA for astronaut health guidelines. Within 5 years of continuous exposure at those levels, the probability of developing radiation-induced cancer rises to near certainty based on current NASA risk models. That is not a mission to Alpha Centauri lasting 80 or 100 years. That is a crew that begins dying from radiation within the first few years of departure. And then there is the threat that requires no collision and no sustained exposure, just a few seconds of being in the wrong part of the universe when something explodes. A gamma ray burst is the most energetic event the universe produces, releasing more energy in seconds than the sun will emit across its entire 10 billion year lifetime. A burst from a source thousands of light years away can still deliver sufficient radiation to strip away a planet's ozone layer. In interstellar space, with no planetary atmosphere and no magnetosphere between the crew and the burst, even a moderately distant gamma-ray event could sterilize the ship's electronics and irradiate the crew fatally in seconds. No warning, no shelter, no survival protocol that makes a meaningful difference. Solar flares from Proxima Centauri itself, which is known to be an extremely active star, far more volatile than our sun, present a similar threat closer to the destination. Think of an interstellar voyage this way. You're driving across the continental United States in total darkness, no headlights, no street lamps, nothing. The road has no guardrails. There are other vehicles on the road that you cannot see and cannot detect until the moment of impact. The speed you are traveling is 100 million kilometers per hour, and every few miles, someone has scattered shards of glass across the pavement that are too small to see, but large enough to shred your tires, except your tires, at this speed, are the hull of a ship containing everything keeping you alive. That is what interstellar space actually is. Not the serene, star-scattered backdrop of science fiction, a killing field moving at you continuously, silently, with perfect indifference to whether you make it or not. If the dust cannot be avoided and the radiation cannot be stopped, does that mean only machines, robots, autonomous probes, artificial intelligence are actually qualified to make this journey? Can biology even survive what physics demands? The engineers who design interstellar ships essentially need to build something simultaneously impenetrable as a nuclear bunker and light as a feather to reach the required speed. It is a problem that physics looks at and laughs. And even if the ship survives when the crew looks back at Earth, they will realize something more painful than death. They have been cut off completely from everything they have ever known. Radio signals travel at the speed of light. That sentence sounds reassuring until you do the arithmetic. When the ship is 2 light-years from Earth, roughly halfway through the journey, a radio message sent from the vessel takes 2 years to reach home. The response, assuming someone on Earth replies immediately, takes another 2 years to return. 4 years. For a single exchange? Not 4 days, not 4 weeks. 4 years of waiting to receive an answer to one question. If a crew member sends a message to their aging parent on the day of departure, and that parent replies the same day they receive it, the crew member will read that reply 4 years later, by which time the parent may already be dead, and the crew member will not know it yet. That is not communication delay. That is the complete collapse of what the word communication means. At the midpoint of the journey, 2 light-years out, a medical emergency produces a scenario so grim it borders on absurdity. A crew member develops symptoms that the ship's physicians cannot diagnose with certainty. They transmit a detailed report to Earth's best medical specialists, full scans, lab results, symptom history, everything. The specialists on Earth receive it 2 years later. They deliberate, consult, run their own analyses, and transmit their recommendations back. The crew receives that response 2 years after that. The total elapsed time 4 years plus. The patient is either recovered, dead, or permanently disabled long before any advice from Earth arrives. Every medical consultation across the entire journey is, by definition, historical correspondence. The doctors on Earth are not treating a patient. They are reviewing a case file from the past. This is not a logistical inconvenience. It is the fundamental severing of the crew from the civilization that launched them. Assume the ship departs in the year 2040. The crew carries with them a complete snapshot of human civilization as it existed at that moment, its music, its science, its political structures, its languages, its values, its understanding of physics, medicine, and engineering. That snapshot is all they will ever truly know. Over the following 100 years, Earth continues. Languages evolve. New scientific frameworks replace old ones. Political systems collapse and reform. Cultural references shift entirely. By the time the ship approaches Alpha Centauri, the civilization that receives their transmissions will be as foreign to the crew as the year 2040 is to someone who lived through the American Civil War. If the crew ever returns, which is itself an enormous, if they will step off the ship as living artifacts, people from another era, speaking slightly outdated language, referencing cultural touchstones nobody remembers, operating on scientific assumptions that may have been overturned decades ago. They will not be returning home. They will be arriving in a future that has no particular reason to recognize them. The absence of real-time news sounds trivial until you sit with what it actually means across a century. Every major event in human history, every war, every pandemic, every technological revolution, every political collapse, every discovery reaches the crew years after it happens. They learn about the death of someone they loved 3 years after the funeral. They receive news of a catastrophic event on Earth when the aftermath is already playing out, and the crisis has either resolved or deepened beyond recognition. They watch history arrive in slow motion, unable to respond, unable to grieve on schedule, unable to celebrate or mourn with the rest of their species in any shared moment of time. They exist in permanent temporal exile. NASA's research into the psychological demands of long-duration spaceflight specifically studies modeling a crewed Mars mission lasting approximately 3 years. Round trip consistently identifies serious psychological deterioration beginning at the 12 to 18-month mark. Crew members in isolation simulations show increasing signs of depression, interpersonal conflict, motivational collapse, and cognitive fatigue well before the halfway point of even a 3-year mission. An interstellar voyage lasting 100 years is 30 to 50 times longer than that Mars baseline. The psychological research does not extrapolate cleanly to those timescales because no framework exists for modeling what prolonged confinement and total isolation do to multiple generations of human beings. We are genuinely in uncharted territory, and the few data points we have are not encouraging. McMurdo Station in Antarctica is frequently cited as the most isolated human outpost on Earth. During the winter over period, a small crew is cut off from the outside world for months at a time, with no possibility of evacuation and limited outside contact. Psychological strain is well documented even there. But McMurdo has email, it has satellite phone calls, it has supply flights that arrive when the season permits, it has the knowledge that the outside world exists, is reachable, and is aware of the crew's presence. An interstellar ship has none of those things. Not one. The crew cannot send a message and receive a reply within their working day, or their working year, or in many cases, their remaining lifetime. The outside world does not just feel far away. It functionally ceases to exist as anything the crew can interact with. Could you go 10 years without internet? Without news? Without contact with family? 10 full years? No updates? No messages? No sense of what is happening to the people and places you left behind. For most people, that question lands somewhere between deeply uncomfortable and genuinely terrifying, and 10 years is 1/10 of the minimum journey. The crew does not get to choose when it ends. They do not get parole. They committed to this the moment the ship left Earth's gravity, and the only exit is arrival or death. The crew of an interstellar ship will be the only people in the history of humanity with absolutely no idea who the President of the United States is, who won the World Cup, or what Taylor Swift released for 100 consecutive years. That is not an exaggeration. That is precisely what total signal isolation means across a century-long voyage. Can you live without the internet? Without news? Without family? For 10 years? And remember, that is only 1/10 of the journey. But isolation is only the beginning. When they finally see their destination after decades in the dark, they will face a physics problem nobody can solve how to stop. Acceleration and deceleration require equal energy. That single sentence contains one of the most punishing constraints in all of interstellar mission planning, and it is worth sitting with until the full weight of it lands. To reach Alpha Centauri in a reasonable time frame, say, 100 years, a ship needs to reach a meaningful fraction of the speed of light. Getting to that speed requires burning an enormous amount of fuel across the first half of the journey. By the midpoint, the ship is moving at its maximum velocity. Now it needs to slow down. Not coast to a stop. There is nothing to coast against in the vacuum of space. It needs to actively decelerate, applying thrust in the opposite direction of travel for the entire second half of the journey. And that deceleration requires exactly as much energy as the original acceleration, which means twice the fuel, twice the mass at launch, which means the engines need to work harder to accelerate that additional mass, which requires even more fuel on top of that, which adds more mass, which demands more fuel still. The Tsiolkovsky rocket equation. The same tyranny that traps chemical rockets in the solar system tightens its grip harder at interstellar scales. Every attempt to solve the deceleration problem by carrying more propellant makes the overall mass budget worse in a way that compounds recursively. Engineers call this the tyranny of the rocket equation, and at interstellar velocities, it is not a tyranny that negotiates. One theoretical alternative avoids the fuel spiral magnetic braking. The idea is to deploy an enormous magnetic field at the ship's bow as it approaches the destination, using the stellar wind and ionized particles streaming outward from Proxima Centauri as a braking medium, essentially dragging against the star's own output to slow down. The physics are plausible in principle. The precision required is extraordinary. The magnetic field would need to be deployed at exactly the right moment, at exactly the right configuration, in an environment the crew has never directly studied, around a star whose behavior is not fully predictable. It has never been attempted. It has never been tested even in scaled simulation. And a miscalculation does not mean a longer journey. It means the ship flies through the Alpha Centauri system at a significant fraction of the speed of light and disappears into the void beyond, with no second chance and no way back. Assuming the ship somehow manages to stop the destination waiting for them, is Proxima Centauri b. Let us talk about what that world actually is. Proxima Centauri b is tidally locked to its star. This means one hemisphere permanently faces Proxima Centauri, receiving uninterrupted stellar radiation around the clock, while the opposite hemisphere faces permanently away, locked in perpetual darkness and extreme cold. There is no sunrise on Proxima Centauri b, no sunset, no cycle of day and night as any human being has ever experienced it. The concept of a day, a rotation, a rhythm of light and dark that has governed every living thing on Earth for 4 billion years simply does not exist there. Half the planet bakes, half the planet freezes. And the line between them, called the Terminator Zone, exists in a state of permanent twilight that might theoretically support more moderate temperatures. That Terminator Zone sounds promising until you consider what drives the weather patterns on a tidally locked world. The permanent temperature differential between the scorching day side and the frozen night side creates pressure gradients of extraordinary violence. Winds along the Terminator would be relentless and potentially extreme, driven by the constant thermal imbalance between the two hemispheres. Climate modeling for tidally locked planets suggests conditions of perpetual atmospheric instability, nothing like the weather system's Earth's rotation moderates and distributes. The Terminator Zone is not a pleasant band of mild climate. It is the battleground between two opposing atmospheric extremes. And then there is the star itself. Proxima Centauri is a red dwarf, an M-type star significantly smaller and cooler than our Sun. Red dwarfs are the most common type of star in the galaxy. They are also, for their size, extraordinarily volatile. Proxima Centauri generates stellar flares, sudden, violent releases of X-ray and ultraviolet radiation with a frequency and intensity that dwarfs anything our Sun produces on a typical basis. In 2016, the same year Proxima Centauri b was discovered, NASA recorded a major flare from Proxima that released radiation at approximately 100 times the intensity of a comparable solar flare from our own Sun. 100 times. That event lasted only a few minutes, but the implication for any surface life or any surface infrastructure is severe. Proxima Centauri does not emit these flares occasionally. It does so regularly, and its planet orbits close enough that the shielding requirements are immense. The atmosphere of Proxima Centauri b is unknown. We have not detected one definitively, and this uncertainty is not a minor detail, it is potentially the entire ballgame. An atmosphere performs two critical functions. It maintains surface pressure that allows liquid water to exist, and it absorbs and scatters incoming radiation before it reaches the ground. Without a sufficiently thick atmosphere backed by a strong planetary magnetic field, the stellar flares from Proxima Centauri would systematically strip away any atmospheric gases over geological time, the same process that left Mars with its thin, inadequate remnant of an atmosphere after the planet lost its magnetic field. Whether Proxima Centauri b has managed to retain an atmosphere against this sustained assault is one of the most important unanswered questions in planetary science, and we do not currently have the answer. Astronomers use the phrase habitable zone for the orbital band where Proxima Centauri b sits. Habitable zone, to an astronomer, means the region where liquid water could theoretically exist on a surface, given the right conditions. It does not mean comfortable. It does not mean safe. It does not mean livable by any standard a human being would recognize. It means the temperature math does not immediately rule out liquid water. That is the entire content of the phrase. You would want to live there, that is a separate question, and the current evidence does not provide encouraging answers. Proxima Centauri b is not a second Earth. It is a rock sitting next to a high-powered microwave, permanently oriented toward the beam, with unknown atmospheric protection and a surface bathed in radiation, pulses 100 times more intense than anything our own star typically delivers. After 100 years of travel, facing every obstacle described across the previous chapters of this journey, the deceleration problem solved by some miracle of engineering, the hull intact, the crew alive. This is what greets them. A tidally locked world orbiting a volatile red dwarf, possibly stripped of atmosphere, almost certainly hostile, waiting with the patient indifference of a universe that never promised any of this would be worth it. After 100 years of travel, if you arrive and find the planet's surface blanketed in lethal radiation with no atmosphere to speak of, what exactly do you do next? But the most terrifying thing is not that planet, it is what happens to the human beings inside the ship. Across generations, on the way there, with a journey lasting 100 years or more, the generation that boards the ship will die on it. Not metaphorically, not as a romantic notion of sacrifice. Literally. The people who strap in at launch, who watch Earth shrink to a blue dot through the viewport, who feel the last tremors of atmospheric turbulence give way to the smooth silence of open space, those people will be buried inside the hull, or their remains processed back into the ship's recycling systems, decades before the vessel reaches its destination. The generation that lands on Proxima Centauri b will be their grandchildren, or their great-grandchildren, depending on the ship's speed. People who were born inside a metal hull, who have never stood on a planet's surface, who have never felt rain or wind or unfiltered sunlight, whose entire known universe is a series of corridors and pressurized chambers moving through the dark. And here is the question that contemporary philosophy has not resolved, and may never resolve cleanly. Those children never agreed to any of it. They did not choose to be born on a spacecraft. They did not sign a mission contract. Nobody asked them whether they wanted to spend their entire lives, every waking moment, every relationship, every ambition, every grief in service of a destination chosen by people who died before they were old enough to form memories. They are, by any meaningful definition, conscripted into a mission by the fact of their birth. The founding generation made the decision. Every subsequent generation inherits it with no exit option. You cannot resign from a generation ship. You cannot emigrate. There is nowhere else to go. Modern bioethics has begun grappling with this problem, and the academic literature is genuinely divided. Some philosophers argue that life aboard the ship, even constrained, can be rich and meaningful, that the mission itself provides purpose and community, and that the children of crew members are no more trapped than children born into any particular culture or circumstance on Earth. Others argue that the deliberate creation of human beings into conditions of permanent confinement, with no possibility of consent and no alternative future available to them, constitutes a fundamental violation of autonomy that no scientific goal can justify. Neither camp has won the argument. The question sits unresolved, and any serious interstellar mission plan that includes a generation ship must eventually answer it or decide to proceed without answering it, which is itself a choice with ethical weight. Reproduction aboard the ship adds its own layer of governance nightmares. To maintain genetic diversity across multiple generations, to prevent the accumulation of harmful mutations and the reduction of immune system variety that follows from a small isolated breeding population, scientists estimate a minimum founding population of somewhere between 500 and 1,000 individuals. Some population genetics models push that number higher still. Below that threshold, inbreeding depression becomes a serious risk within just a few generations. Above it, the ship's life support requirements scale accordingly. But maintaining a stable population is not simply a matter of having enough people at launch. Uncontrolled reproduction means population growth, and population growth inside a closed system means escalating resource consumption, more food, more oxygen, more water, more medical care, until the ship's systems can no longer support the number of people aboard. Controlled reproduction is the alternative, which immediately raises a different set of questions. Who decides how many children a person may have? Who determines which genetic pairings are encouraged and which are discouraged for the sake of diversity? Who enforces those decisions across generations? In a community where the governing authority is entirely self-contained and has no external checks on its power, a generation ship, taken to its logical conclusion, requires some form of reproductive governance that would be considered authoritarian by any standard operating on Earth today. And then sitting underneath all of these problems, quiet and devastating, is the waiting paradox. Imagine humanity launches Ship A in the year 2100, using the best propulsion technology available at that time, achieving 5% of the speed of light. The mission is extraordinary. The sacrifice is immense. The crew boards, knowing their grandchildren will be the ones to arrive, they go anyway, because the technology is ready and the decision has been made. 50 years later, in the year 2150, a breakthrough in propulsion physics allows engineers to build Ship B. This new vessel achieves 15% of the speed of light, 3 times faster than Ship A. Ship B launches. The math is simple and merciless. Ship A has been traveling for 50 years at 5% of the speed of light. Ship B launches 50 years later at 15% of the speed of light. Ship B overtakes Ship A somewhere in the interstellar void and arrives at Alpha Centauri years, possibly decades, before Ship A does. The crew of Ship A, or rather, their grandchildren, watch a newer ship pass them. They arrive second. They arrive with older technology. They arrive having made every sacrifice, borne every hardship, buried every person who launched with the mission, and the civilization that sent them has already been there, already established contact with the destination, already moved on. So why launch Ship A at all? Why not wait for better technology? Because if you always wait for better technology, you never go. The next breakthrough is always theoretically possible. The next generation of propulsion is always potentially just decades away. The rational case for waiting is always available, and it always sounds reasonable. And if you follow it to its conclusion, you wait forever while the stars remain unreached. The paradox has no clean solution. Launch too early, and you sacrifice generations for a mission that gets overtaken. Wait too long, and you never launch at all. It is a logical trap with no exit, and it could paralyze every interstellar launch decision humanity ever attempts to make. The waiting paradox is essentially the cosmic version of picking the wrong line at the airport. except instead of wasting 20 minutes watching the lane next to you move faster, the consequence is 100 years of human lives consumed for a mission that a faster ship renders partially redundant. If you knew before departure, with certainty, that a faster ship launched 50 years after you would arrive at Alpha Centauri, before your grandchildren did, would you still stay aboard? Would you still go? And when the crew has paid that price, lived and died inside that ship across generations, what waits for them at the destination might be crueler than the journey itself. After 100 years of continuous operation, the landing system fails. Not a dramatic explosion, not a cascading catastrophe announced by alarms, just a component, one critical component among tens of thousands that has reached the end of its functional lifespan after a century of vibration, thermal cycling, and radiation exposure, and has quietly stopped working. No spare parts exist. The manufacturing specifications for that component exist only in databases on a planet 4.24 light-years away. A distress signal sent to Earth will arrive in 4 years. Any response, assuming Earth still has the institutional memory and technical capability to help, will arrive 4 years after that. 8 years of waiting for guidance on a problem that may have already killed the mission within days of its onset. The crew is in orbit around Alpha Centauri. They cannot land. They cannot return. The fuel for a return journey was never part of the mass budget, because a return was never realistically planned. They circle a star system that is not their own, inside a ship that has just exceeded its designed operational limits, with no rescue coming and no timeline for resolution. This is not science fiction. This is a straightforward engineering probability applied to a machine operating beyond any precedent for duration and environmental stress. Components fail. After a century in deep space, the realistic question is not whether anything will fail, it is how many things will fail, and whether the crew can improvise solutions from whatever materials remain aboard. Scenario 2 is quieter, and in some ways, more devastating. The ship arrives intact. The crew is alive. They achieve orbit around Proxima Centauri b and begin their surveys. The data comes back clear, no atmosphere of any significance, no liquid water on the surface. The planet's magnetic field is too weak to have protected against Proxima Centauri's stellar flares. And over billions of years, those flares have done exactly what the models feared: stripped the atmosphere away, leaving a desiccated, radiation-scoured rock exposed directly to one of the most volatile stars in the local neighborhood. The surface temperature on the day side is extreme. The night side is frozen solid. The terminator zone is a wind-blasted margin between two uninhabitable extremes. The mission's entire justification, the possibility of a habitable world at the nearest star, is gone. What remains is a scientific expedition to a dead planet. The crew collects rock samples. They deploy instruments. They transmit everything back to Earth, knowing the signal will arrive in 4 years, and that they will never know what Earth does with the information. They are the most isolated scientists in the history of the species, studying a world that has nothing to offer human settlement, surrounded by the remains of a journey that consumed generations. The third scenario begins with a discovery that would be the most significant moment in the history of humanity, and immediately becomes an ethical emergency with no procedure to follow. The crew's instruments detect complex organic structures in the rock, not contamination from the ship, not abiotic chemistry. Structures with the unmistakable signature of biology, or at least, of something that was once alive. Fossilized remnants of organisms that existed on Proxima Centauri b before the stellar flares destroyed the atmosphere. Life arose here. Life evolved here. And then something ended it. The Planetary Protection Protocol, the internationally agreed framework governing how spacecraft avoid contaminating other worlds or bringing contamination back, requires that the crew not compromise the site, no direct contact without containment procedures. no sample collection without sterile protocols. But the crew has already been there. Their ship has already been shedding microscopic particles since orbital insertion. Whatever contamination was going to happen has already begun, and any communication with Earth about what to do next takes 8 years for a round trip. Every decision falls to the people in that ship, in that moment, without oversight, without authorization, without the full weight of humanity's scientific community available to guide them. They are making the most consequential choices in the history of science completely alone. Scenario 4 is the one that no official protocol fully addresses. Because no government has been willing to finalize one, the sensors detect something that is not geological, not biological in the fossilized sense, something structured, something that exhibits the mathematical regularity of engineering rather than the irregular patterns of natural formation. The crew is looking at evidence of a civilization or the remains of one, and they have no script. The United Nations has debated frameworks for post-detection protocols for decades without reaching binding international consensus. The crew must decide, in real time, with a 4-year signal delay, making Earth's input irrelevant to any decision requiring immediate action, how humanity will respond to the most transformative discovery in its history. They are not diplomats. They were not selected for this scenario. Nobody was, because nobody truly planned for it. Scenario 5 requires no external discovery to be devastating. The crew knew before departure that the fuel budget for a return journey was not included. The mission is one way. That decision was made on Earth by people who calculated that the mass required for return propellant would make the outbound journey impossible, and that the scientific and exploratory value of a one-way mission justified the terms. The crew accepted those terms, but acceptance in theory on a launch pad on Earth with the sun overhead and the weight of civilization's hopes behind you is a different thing from acceptance in practice orbiting a cold red star, 4.24 light years from the only world your species has ever called home, knowing that this is simply where your story ends. Climbing Everest in total darkness, with no rope, no map, and no rescue helicopter, and discovering, when you finally reach what you thought was the summit, that the top of the mountain collapsed long ago, and what you have climbed to is just a ledge above a void. Of the 5 scenarios: permanent system failure, a dead planet, the discovery of extinct life, contact with another civilization, or the knowledge that you will never return, which one do you think is the most terrifying? The United Nations framework for responding to confirmed extraterrestrial contact is still being drafted and debated, which means that if the crew actually meets someone at Alpha Centauri, they will be improvising based on personal judgment and whatever common sense they can muster in the moment. Let us hope humanity's representative to the cosmos is not having a bad day. But all of these risks share one common denominator: cost. And the real question is not whether we can do this. It is why we would ever want to. No official price tag exists for a crewed interstellar mission. No government agency has published a line item budget. No aerospace contractor has submitted a formal bid. The reason is simple. The engineering requirements are so far beyond current capability that any precise estimate would be, at best, an educated projection built on assumptions stacked on assumptions. What academic researchers and mission planners have produced are ranges, and those ranges are staggering. Conservative estimates place the cost of a crewed mission to Alpha Centauri, using significantly advanced but theoretically achievable technology, at somewhere between $100 billion and $1 trillion. That is not a typo. 1 trillion, the lower end of that range, already exceeds the gross domestic product of most countries on Earth. The upper end approaches the total annual military spending of every nation on the planet combined. To put those numbers in context that feels more grounded, the entire Apollo program, Every rocket, every mission, every astronaut, every ground crew, every year of development from 1961 to 1972 cost approximately $280 billion in today's adjusted value. It was the most expensive peacetime scientific undertaking in American history. And it put 12 human beings on the moon. The International Space Station, constructed over more than a decade with contributions from 15 nations, has cost approximately $150 billion to build and operate. An interstellar mission would be a multiple of both of those figures combined, sustained over decades or centuries of development, with no guarantee of success and no possibility of a quick return on investment. The case against spending that money is not frivolous. It deserves to be stated clearly and taken seriously. $1 trillion could fund the complete elimination of extreme global poverty, the kind where people live on less than $2.15 per day for decades. It could accelerate renewable energy deployment to a scale that meaningfully addresses climate change within a generation. It could fund cancer research, Alzheimer's research, pandemic preparedness infrastructure, clean water access for the 1 billion people who currently lack it. Every dollar spent on an interstellar mission is a dollar not spent on problems that are killing people right now, today, on the planet we already live on. The ethical weight of that trade-off is real, and anyone who dismisses it is not engaging honestly with the question. Furthermore, the probability of mission failure with current technology is, as every preceding part of this story has made clear, not negligible. It is the baseline expectation. A $1 trillion mission with a high probability of catastrophic failure and no clear return within several centuries is not an investment by any conventional definition. It is an act of faith, expensive, irreversible faith in a future that may not materialize. And yet, Stephen Hawking, arguably the most recognized theoretical physicist of the late 20th and early 21st century, returned repeatedly to the same warning before his death in 2018. He stated it in interviews, in lectures, in public addresses spanning decades. Humanity must become a multiplanetary species and, eventually, a multistellar one, or it faces eventual extinction, not as a remote philosophical possibility, as a statistical inevitability. Earth is a single point of failure for the entirety of human consciousness. One large asteroid impact, one supervolcano, one engineered pandemic, one sufficiently catastrophic climate shift. Any of these events, occurring on a long enough timeline, removes humanity from the universe permanently, not just from Earth, but from existence. Full stop. The economic argument for staying home assumes that Earth will remain habitable indefinitely. That assumption has no geological or astronomical support whatsoever. It is comfort, not evidence. Beyond survival, the practical returns from space programs have consistently exceeded expectations in domains nobody anticipated. GPS technology, now embedded in every smartphone and navigation system on the planet, emerged directly from satellite programs developed for space exploration. MRI scanning technology traces its origins to research conducted for space medicine. Memory foam, scratch-resistant lenses, water filtration technology, the miniaturization of electronics that made the personal computer revolution possible. All of these are spin-offs from programs that critics at the time called wasteful and impractical. The engineering problems posed by interstellar travel are so extreme that solving even a fraction of them would generate technological advances across materials, science, medicine, energy, computing, and biology that are impossible to fully anticipate from where we stand today. And underneath all of the economic and strategic reasoning sits something older and less rational, something that does not respond well to cost-benefit analysis because it was never designed to. Homo sapiens left Africa, not because the continent was inhospitable, not because there was a documented resource shortage, not because a committee evaluated the risks and determined that migration was the optimal strategy. They left because some members of the species walked toward the horizon instead of away from it. They crossed land bridges to continents they could not see. They built boats and sailed into open ocean without knowing what was on the other side. They crossed mountain ranges, deserts, ice fields, not because survival required it in every individual case, but because the drive to go further appears to be embedded in the species at a level that precedes deliberate reasoning. Every continent was once an unknown. Every ocean crossing was once considered suicidal. The argument that we should stay where we are because the destination is uncertain and the cost is high has been made at every expansion point in human history. It has never won permanently. Do you think the cost, hundreds of billions of dollars, is too high? Or is it small compared to ensuring that human consciousness does not end with a single planetary catastrophe? Debating the cost of interstellar travel is roughly equivalent to early humans sitting around a fire, arguing about whether investing resources in these so-called boats was really worth it when staying in the cave was working fine. Technically survivable, yes. But something in the species has never been satisfied with survivable. But suppose humanity goes and actually arrives. What happens to the species itself afterward? The answer will change the definition of human forever. The descendants of an Alpha Centauri colony will not be quite human. Not immediately, not obviously. But the process will begin on the day the ship launches, and it will not stop. Evolutionary divergence is not a science fiction concept. It is the mechanism by which every distinct species on Earth came to exist, operating across timescales that seem long from a human perspective, but are routine in the history of life. Separate a population, change its environment, give it enough generations, and the biology changes. The only question for an interstellar colony is how fast and in which directions. Start with gravity. If Proxima Centauri b has surface gravity meaningfully different from Earth's either higher or lower, the human body will adapt across generations. Lower gravity reduces the mechanical load on bones and cardiovascular systems, leading to reduced bone density, altered muscle mass distribution, and changes in how the heart manages fluid circulation. Higher gravity does the opposite, selecting over generations for denser bones and more powerful musculature. Neither adaptation happens consciously. It happens because individuals whose physiology better matches the environment survive and reproduce at higher rates than those whose physiology does not. That is natural selection, operating exactly as it always has, with a new environment setting the parameters. Radiation exposure is a more direct driver of genetic change. Different radiation environments produce different rates and types of DNA mutation. Most mutations are neutral or harmful. But across enough generations, a small fraction of mutations that provide radiation resistance will accumulate in the population if the environment selects for them. The genome of the colony's descendants, 10,000 years from now, will carry the signature of Proxima Centauri's radiation environment in ways that Earth humans' genomes do not. Diet changes the microbiome, the ecosystem of bacteria living in the human gut, and the microbiome influences everything from immune function to neurological development to emotional regulation. A population eating different foods, grown in different soils under different atmospheric conditions, will develop a different microbiome within generations. The ripple effects through physiology and psychology are only beginning to be understood by science. But the direction is clear. Change the diet. Change the gut. Change the person. The circadian rhythm, the internal biological clock calibrated over millions of years to Earth's 24-hour day and night cycle, will encounter a tidally locked world where one hemisphere has no night and the other has no day. Whatever rhythm the colony develops in the Terminator Zone, it will not be the rhythm that shaped every aspect of human hormonal function, sleep architecture, and cognitive performance across evolutionary history. Something will adapt. What it becomes is genuinely unknown. After 10,000 years of these pressures operating simultaneously, gravity, radiation, diet, circadian disruption, and the founder effect narrowing the initial gene pool, the population on Proxima Centauri b may no longer be capable of producing fertile offspring with Earth humans. That is the biological definition of a separate species, not a cultural distinction, not a philosophical category, a reproductive barrier established by the ordinary machinery of evolution operating in an ordinary way over an ordinary timescale. Researchers have discussed this possibility in serious academic literature under the informal designation Homo Centauri, not as a prediction of a specific outcome, but as an acknowledgement of where the biology points if the colony persists across geological time. We would not have sent colonists to another star. We would have created a new form of intelligent life, and it would be our children who became it. The governance problem does not wait 10,000 years to become urgent. It begins the moment the ship leaves Earth orbit. Who has authority over a colony 4.24 light-years away? Any nation or organization that claims jurisdiction faces an immediate, physics-imposed limitation. Every directive, every law, and every judicial ruling takes 4 years minimum to reach the colony. Every response from the colony takes another 4 years to return. A legal dispute that could be resolved in a day on Earth takes 8 years of signal transit time before the relevant parties have even exchanged opening positions. By the time Earth's governing bodies have deliberated and responded, the situation on the colony will have evolved multiple times in directions that the response can no longer address accurately. The colony, therefore, is self-governing by necessity, not by choice, not by rebellion, not by political philosophy, by physics. No meaningful external authority can operate at a 4-year communication delay. The colony will develop its own legal systems, its own resource allocation mechanisms, its own methods for resolving internal conflicts, its own values and cultural norms shaped by an environment that Earth humans have never experienced. It will become, over time, a civilization related to Earth civilization, the way a child is related to a parent, but distinct, autonomous, and increasingly shaped by its own particular world. America was a British colony separated from London by a journey of several weeks by ship. That delay was enough. The cultural, economic, and political divergence that built up across a century and a half of imperfect communication and governance at distance produced the American Revolution. The colonists did not begin as separatists. The separation was produced by the simple mechanics of distance and time operating on human society. 4.24 light-years is not several weeks. It is 4 years at the speed of light. The divergence that produced the American Revolution would, at that communication delay, be compressed and intensified beyond any historical precedent. There is no mechanism, legal, military, or diplomatic, that can maintain meaningful authority over a self-sustaining colony at that distance. No interstellar court exists. No interstellar peacekeeping force could ever deploy in response to a crisis. By the time any enforcement mechanism from Earth arrived at Alpha Centauri, the situation that prompted it would be ancient history. For the first time in the history of the species, humanity would not be a single thing. It would be at least 2 things diverging biologically, culturally, technologically, and linguistically, with no shared real-time experience, no common authority, and no mechanism for reunion. The word human would need an asterisk, or perhaps a new word entirely. If our descendants evolve into something that can no longer biologically reproduce with us, are they still human? We are essentially planning to create aliens, and those aliens will be our own grandchildren. Which is, when you think about it, the most unexpected answer anyone has ever proposed to the Fermi paradox. But before worrying about the evolutionary future, there is one fundamental engineering problem that almost nobody thinks about. How do you actually navigate to a target that is constantly moving through three-dimensional space? Alpha Centauri is moving. That fact alone reframes everything about how an interstellar mission must be planned, because it means the target you are aiming at today is not where it will be when you arrive. The Alpha Centauri system moves relative to our Sun at approximately 25 kilometers per second. Over the course of a 100-year voyage, that motion carries the system roughly 78 billion kilometers from its current position, farther than the distance from the Sun to Neptune, crossed twice over. A navigator who points the ship at where Alpha Centauri sits today and fires the engines is not navigating to the destination. They are navigating to a point in empty space that the destination will have vacated long before the ship gets there. Interstellar navigation requires aiming at where the target will be a calculation that must account for the star system's velocity, the ship's velocity, gravitational influences from intervening mass, and the cumulative effect of every course correction made along the way. It is not like shooting an arrow at a stationary target. It is more like throwing a dart across a room at a fly that is moving in 3 dimensions, while you yourself are also moving, and the room's geometry is subtly shifting around you. There is no GPS in interstellar space, no network of satellites broadcasting reference signals, no ground station sending positional updates. The ship must calculate its own trajectory continuously using stellar navigation identifying reference stars, measuring their positions relative to each other, and triangulating the ship's location within that framework. This is a method with deep historical roots in maritime navigation, refined for space by observational astronomy, and it works reasonably well at low velocities. At a significant fraction of the speed of light, it stops working cleanly. At high velocities, 2 optical effects distort the star field that the crew observes. The Doppler effect shifts the frequency of incoming starlight stars ahead of the ship appear bluer than normal. Stars behind appear redder, changing their spectral signatures in ways that interfere with precise identification. Aberration, a separate effect, shifts the apparent positions of stars toward the direction of travel, compressing the entire forward field of view and stretching the rear. The star map the crew sees at 10% of the speed of light is meaningfully different from the star map used to plan the mission from Earth. The reference points are still there, but they have moved, and the corrections required to compensate for Doppler shift and aberration must be applied with extreme precision to every navigational calculation. A small error in that compensation propagates forward through every subsequent calculation, which brings the question of cumulative error into sharp focus. A directional error of 0.001 degrees at launch an angle so small it is essentially invisible to human perception translates over a distance of 4.24 light-years into a positional error of millions of kilometers at the destination. The ship misses not just the planet, but the entire inner system of Alpha Centauri by a margin that makes course correction wildly expensive in fuel and time. Navigators must therefore make continuous corrections throughout the journey, each one consuming propellant from a budget that was already barely adequate when the mission launched. Each correction is also based on observational data that carries its own uncertainty. The errors do not simply accumulate, they interact, each correction introducing a small new error that the next correction must partially address, creating a feedback loop of decreasing precision that must be managed with extraordinary care across decades of flight. No human navigator has ever faced a problem of this duration and complexity. No automated system has ever been tested across timescales approaching a century. The navigational software running on the ship at departure was written by engineers who are dead by the time the critical arrival calculations are being executed. Its assumptions, its error handling routines, its edge case behavior. All of it was designed for a mission profile that may have diverged from reality in ways the original programmers could not anticipate. And while the navigation system is managing all of this, the physical structure of the ship is conducting its own slow deterioration. Metal fatigue is the unglamorous enemy of long-duration engineering. Every vibration from the engines, from mechanical systems, from the thermal expansion and contraction of structural members cycling through temperature changes, works on the metal in ways that are individually tiny and collectively devastating over time. Microscopic cracks form at stress concentration points. They grow slowly, invisibly, through material that appears solid and intact. On Earth, aircraft are inspected for metal fatigue on strict schedules because engineers know that even well-maintained structures develop these cracks and must be caught before they reach critical size. An interstellar ship has no maintenance schedule from outside. The crew can inspect accessible surfaces, the deep structural members embedded in the hull, the load-bearing elements at the core of the ship's skeleton. Those are not easily reached, and any crack found there cannot be repaired by calling in a specialist. Thermal stress operates in parallel. One face of the ship, whichever side is oriented toward a heat source, whether the receding sun or internal reactor systems, operates at temperatures hundreds of degrees higher than the opposite face. Metal expands when heated and contracts when cooled. Across a structure the size of a city block, that differential expansion and contraction produces mechanical stress that never stops. The joints, the welds, the fasteners, everything that holds the ship together is being worked continuously by forces that engineering can mitigate, but never fully eliminate. Radiation degrades materials in ways that are distinct from mechanical stress and thermal cycling, but no less damaging. Plastics, rubber compounds, polymer composites, the seals around airlocks, the insulation on electrical cables, the gaskets in fluid systems, the coatings on sensitive instruments. All of these materials break down faster in high radiation environments than they do under normal terrestrial conditions. Polymer chains fracture. Rubber loses its elasticity. Seals that were watertight at launch become permeable over decades of radiation exposure. The ISS, maintained continuously by rotating crews, resupplied with replacement components on a regular schedule, operated by a global support infrastructure, has been in service for more than 25 years and is already showing signs of structural aging that concern engineers planning its continued operation. An interstellar ship needs to function 5 to 10 times longer than the ISS with zero external support, zero replacement parts from Earth, and zero possibility of docking at a maintenance facility. Designing an interstellar ship is equivalent to demanding that a car drive nonstop for 100 years, through the worst terrain imaginable, without ever visiting a garage once, and without any single component being permitted to fail. Your phone breaks after 3 years. Your wireless earbuds lose their battery capacity after 2. The fridge in your kitchen, if you are lucky, lasts 15 years before something goes wrong. We are talking about building a machine that must operate flawlessly for 100 years in the most hostile environment in the known universe. This is why aerospace engineers working on long-duration mission concepts do not sleep well. Do you believe that anything built by human hands could operate perfectly for 100 continuous years without a single failure? If the ship's structure can hold together the thing most likely to collapse, first is the one thing that cannot be engineered around the human mind. In 2010, 6 volunteers sealed themselves inside a series of interconnected modules in Moscow and did not come out for 520 days. The Mars 500 experiment, conducted jointly by the European Space Agency and Russia's Institute of Biomedical Problems, was the most ambitious psychological isolation simulation ever attempted. The crew followed mission protocols, performed scientific tasks, maintained communication with a simulated time delay, and lived in conditions designed to approximate a crewed Mars mission as closely as possible without leaving the ground. By the end, the psychological data was unambiguous. The crew showed measurable deterioration across multiple indicators: depression, chronic sleep disruption, progressive loss of motivation, increasing passivity, social withdrawal within the already tiny group. The most significant declines appeared in the later stages of confinement, not the early ones, suggesting that time itself, as it accumulated, became a force pressing down on the mind in ways that initial adaptation could not fully counter. That was 520 days. A generation ship voyage lasts roughly 36,500 days at minimum, 70 times longer. The Mars 500 findings do not extrapolate to that timescale in any clean, linear way, because no psychological framework exists for modeling what happens to human beings across multiple generations, confined in a closed environment for a century. We are in territory where the research simply stops, and what lies beyond is educated inference built on concerning foundations. Leon Festinger's foundational work in social psychology, published in 1950, established something that subsequent decades of research have consistently supported: small, isolated groups inevitably develop internal factions. Not because the individuals involved are poorly selected or insufficiently committed. Because the formation of subgroups, the emergence of status hierarchies, and the competition for influence within a constrained social environment are features of human social behavior that appear across cultures, contexts, and levels of awareness. No amount of pre-mission team building eliminates these dynamics. They are not a bug in the software of human sociality. They are part of the operating system. On a ship with no outside world to provide shared reference points, no cultural novelty to redirect attention, and no exit for people who find themselves in conflict, these dynamics have nowhere to discharge. They cycle back into the group, compressing and intensifying over years and decades. The internal catastrophe scenarios that follow from this environment are not hypothetical. They are probability assessments. A hull breach, a rupture in the ship's pressure envelope, requires coordinated action by multiple crew members within seconds. Seal the section, confirm pressure integrity, account for personnel. The procedure is well defined. Executing it correctly requires that the people involved are functioning under stress as a coordinated team, not as individuals whose interpersonal relationships have been strained by years of proximity and conflict. Emergency performance degrades in proportion to the psychological state of the responders. In a crew that has been confined together for 20 or 30 years, the psychological overhead that comes with every interpersonal history, every unresolved conflict, every established grievance, all of it is present in the room during the emergency. The gap between a drill and the real event is always significant. In that environment, after that duration, the gap may be much wider than mission planners projected. Disease transmission in a closed, recirculating atmosphere is a threat that the COVID-19 pandemic made viscerally intuitive for a global audience. Now, remove the ability to open a window. Remove the option to isolate in a separate building. Remove the possibility of receiving outside medical support within any relevant time frame. A novel pathogen or a known pathogen that has mutated within the ship's population over years of circulation encounters a community with no external refuge and no medical reinforcements available. The ship's medical capacity, however well stocked at launch, was finite. Pharmaceutical supplies designed for a century of operation face the additional challenge that most medications have: shelf lives of 2 to 5 years. Restocking is not possible. Reformulating drugs in a ship laboratory, synthesizing replacements from raw chemical precursors requires pharmaceutical expertise and equipment that may or may not have survived intact. The medical response to a serious outbreak, late in the voyage, could be working with degraded supplies, degraded equipment, and a medical team that is itself affected. Documented incidents at Antarctic research stations and other extreme isolation environments confirm that violence between crew members is not a theoretical risk invented for dramatic effect. It is a recorded outcome. The circumstances that produce it: extended confinement, status conflict, perceived injustice within a small community, the psychological pressure of an environment that offers no relief, are all present on a generation ship, amplified by duration that no polar expedition has approached. The second and third generations inherit all of this without the consolation of having chosen it. Research on third culture kids' children raised between two cultural worlds, belonging fully to neither, consistently identifies elevated rates of identity crisis, ambivalence, and psychological instability compared to populations with clear cultural grounding. Children born on the ship do not belong to Earth. They have never seen it, cannot return to it, and know it only through records that grow less current with every passing year. They do not belong to Alpha Centauri either. They have never seen it and are not yet there. They belong to the ship, to the corridors, the recycled air, the artificial lighting, the specific social world of a community that is itself under chronic stress. What that does to a developing psychology across not one child, but multiple generations of children, for a century, is a question that has no precedent and no clear answer. NASA is currently conducting serious research into optimal interior architecture for reducing crew conflict in long-duration missions. That is the actual subject of funded scientific inquiry, designing a living space attractive and varied enough that 1,000 people do not come to hate each other over the course of 100 years. This is the most consequential interior design problem in the history of human construction, and calling it a feng shui question would be funnier if the stakes were not so absolute. Building a generation ship is not planning a long voyage. It is building an entire society from scratch, inside a metal enclosure, with no escape route and no outside assistance, and then hoping that society does not destroy itself before it reaches the destination. If you were born on that ship, if the only world you had ever known was those metal walls, that recycled air, that community of people under permanent stress, what do you think that would do to you? But suppose everything holds. The ship survives. The crew remains intact. They arrive. What actually waits for them when human beings set foot on another world for the first time in history? The first step onto the surface of Proxima Centauri b will not look like the moon landing. No white suit gleaming against a gray plane. No static-filled transmission cutting through to a world holding its breath. The crew will descend in a lander that has been sitting in the ship's hangar for the better part of a century. Its components inspected and re-inspected by people who were not alive when it was built, following procedures written by engineers whose names are now only in the historical record. The landing itself, the actual physical act of touching down on the first world outside our solar system that any human being has ever stood upon, will be a technical exercise performed by a crew that has spent its entire life preparing for a moment none of them have ever experienced, on terrain none of them have ever seen directly, in an environment none of them fully understand. The gravity may feel wrong immediately. If Proxima Centauri b's surface gravity differs meaningfully from Earth standard, and it very likely does, given the planet's uncertain mass and composition, bodies that have spent years adapting to the ship's rotational gravity will encounter yet another adjustment. Muscles calibrated for one gravitational environment performing in another. The inner ear recalibrating. The cardiovascular system redistributing fluid in response to a new set of demands. The first steps on another world may be cautious and uncertain, not from awe, but from the simple biological reality that the body is solving a new equation in real time. The atmosphere question will have been partially answered from orbit, but partially is not fully. If any atmospheric gases are present, the composition is not Earth standard. The crew breathes recycled ship air through a sealed helmet. The sense of arrival, the primal, embodied sense of being somewhere new, arrives filtered through life support equipment. No smell of alien soil, no feel of wind on skin, no unmediated contact with the environment. Just the sound of the breathing apparatus, the slight resistance of the suit with every movement, and the view through a visor of a landscape no human eye has ever processed before. The sky, if there is atmosphere enough to scatter light, will be wrong. Proxima Centauri is a red dwarf, emitting the majority of its light in the red and near-infrared spectrum. The sky above Proxima Centauri b, where it exists, will not be blue. It will be something in the range of deep red, or rust, or perhaps a dim reddish violet, depending on atmospheric composition and density. The star itself, Proxima Centauri, will hang fixed in that sky, never rising, never setting. Larger in apparent diameter than our sun appears from Earth, but dimmer, casting a light that is fundamentally different in color and quality from anything the human visual system evolved to process. Everything looks different under that light. The shadows fall at permanent angles. There is no golden hour, no blue dusk, no dawn. Just that red dwarf, motionless, burning. And because the planet is tidally locked, if the crew has landed in the Terminator Zone, the only region where conditions might be survivable, the star sits perpetually near the horizon, a permanent sunset that never ends and never begins. A sky divided between the blazing day side and the absolute darkness of the night side, with the crew positioned at the narrow margin between them. Then the instruments find something in the rock. Not immediately, not on the first survey, but in the course of drilling core samples from geological formations that have been stable for hundreds of millions of years. The analysis comes back with a signature that stops the team cold: complex organic carbon structures. Not simple chemistry, not the abiotic carbon compounds that form under certain geological conditions without the involvement of life. These structures have the molecular architecture of biology, repeating patterns, information-dense configurations, the kind of complexity that, on Earth, has only one known source. Something lived here, not now. The planet's surface is sterile. Whatever destroyed the atmosphere ended any surface life long ago. But deep in the geological record, in rock laid down before the atmosphere was stripped, before the stellar flares scoured the surface clean, there are the mineralized remnants of organisms, fossils, in the broadest sense of the word, evidence that life arose on Proxima Centauri b, developed biological complexity, and then at some point in the planet's history was ended. By radiation, by atmospheric loss, by the slow, indifferent violence of a volatile star doing what volatile stars do over billions of years. Life existed at another star, and it died. The implications are enormous in two directions simultaneously. It means life is not unique to Earth, that the chemistry of biology, given the right starting conditions, can emerge elsewhere in the universe. That single discovery rewrites the foundational question of whether humanity is alone. But it also means that planetary habitability is not permanent, that a world can support life and then lose the conditions for it, and then be left as a sterile memorial to what was once there. Proxima Centauri b did not fail to produce life. It produced life and then killed it. The question of which trajectory Earth is on, whether it is in the phase of supporting life or approaching the phase of ending it, takes on a new and uncomfortable weight when you are standing on the evidence of the second option. The Planetary Protection Protocol, which governs how crew members interact with extraterrestrial environments, requires that no bare skin contact the surface, no breathing of local atmosphere, even if trace amounts are present. Every sample collected must be sealed in sterile containers and moved through contamination barriers before entering any shared space. The crew does not touch this world. They observe it, measure it, sample it through layers of equipment designed to keep Earth biology separate from whatever exists here. But the honest question that cannot be fully resolved is whether that separation was already compromised during landing. Every spacecraft sheds particles. Seals are imperfect. The descent vehicle, moving through whatever trace atmosphere exists, may have introduced Earth microorganisms to the surface before the crew set foot anywhere. And the crew's own bodies, even inside suits, are sources of biological material that leaks through imperfect barriers in ways that are difficult to quantify and impossible to fully prevent. The Planetary Protection Protocol was designed to minimize contamination. It cannot guarantee zero contamination. On a world that turns out to have hosted its own life, even extinct life, the question of whether the crew has introduced foreign biology into an archaeological record of cosmic significance is not paranoia. It is a legitimate scientific concern with no clean answer available. Standing on the surface, the crew member who looks up and searches the sky for the sun will need to know which direction to look, because the sun, from 4.24 light-years away, is not the overwhelming presence it is from Earth. It is a star, one of thousands visible in the sky. A bright one, it would rank among the more prominent stars visible to the naked eye from this distance, but a star nonetheless. Indistinguishable in kind from every other point of light scattered across that alien sky. Every war in human history, every work of art, every love story, every religion, every scientific discovery, every catastrophe and triumph and ordinary day lived by every human being who ever existed, all of it happened on that star. That specific pinprick of light, no different in appearance from its neighbors. Holding in orbit one small world where, for a few 100,000 years, a species became conscious and started asking questions about where it came from and where it was going. No language developed on that world has the right words for what that moment feels like. The languages were built for human-scale experience. This is not human scale. Every concept available small, vast, humbling, lonely, beautiful, arriving slightly wrong, slightly insufficient, slightly too domesticated for what the moment actually contains. The crew member stands there with the full weight of the journey behind them. Every sacrifice, every death, every generation that did not live to see this and looks at the star that made them. Now, just a light in someone else's sky. If you were the first human being standing on the surface of Proxima Centauri b, what would your first words be? With a 4.24-year signal delay, when the crew transmits their arrival message back to Earth, a child born at the exact moment that message is sent will be starting 4th grade before anyone on Earth receives it. The celebration will be very delayed. Throughout everything you have just read, one assumption has quietly governed the entire conversation. We have treated Alpha Centauri as the destination, the endpoint, the summit, the thing humanity is reaching toward, the great ambition of interstellar travel, the ultimate test of our species, the horizon that justifies every sacrifice and every technological leap discussed across these pages. Alpha Centauri has been the answer to the question of where we are going. But nobody told you the part that comes after that assumption collapses. Alpha Centauri, the nearest star system to our sun, the closest neighbor in the entire cosmic neighborhood, the target of breakthrough starshot and generation ship proposals and decades of scientific discussion, is not the destination. It is not even close to being the destination. It is the first step, the very first, the equivalent of walking to the end of your driveway and calling it a road trip. The Milky Way galaxy contains approximately 400 billion stars. The distance from one edge of the galaxy to the other is roughly 100,000 light-years. Alpha Centauri sits 4.24 light-years from Earth. Do the arithmetic. Reaching Alpha Centauri covers approximately 0.004% of the diameter of our own galaxy. We have not left the neighborhood. We have not left the block. We have not left the property. Everything discussed in this entire story, every obstacle, every sacrifice, every century of travel delivers us to a point that is, in galactic terms, essentially still here. And the Milky Way is not the universe. Modern telescopes, the Hubble Space Telescope, the James Webb Space Telescope, and the observational infrastructure built over the past century of astronomy have revealed a cosmos containing an estimated 2 trillion galaxies within the observable universe. 2 trillion. The nearest large galaxy to our own is Andromeda, officially designated Messier 31. It sits approximately 2,537,000 light-years away. Not 4 light-years, not 100,000 light-years, 2,537,000 light-years. Based on everything physics currently understands about the structure of reality, traveling to Andromeda is not merely difficult, it is permanently, categorically impossible for any physical object, regardless of technology, regardless of time available, regardless of any propulsion system conceivable within known physics. The universe is expanding. The space between galaxies is growing. Andromeda is close enough and moving toward us fast enough that it will eventually collide with the Milky Way in approximately 4.5 billion years. But the galaxies beyond it are receding faster than light itself can cross the distance. And no ship traveling at any speed can catch a destination that is moving away faster than it can be approached. Most of the universe is, by definition and by physics, permanently beyond reach, not currently unreachable, not unreachable pending better technology, permanently, structurally, forever unreachable. And now, the final trap closes. Everything described above the 2 trillion galaxies, the 100,000 light-year span of our galaxy, the Andromeda collision, all of it refers only to the observable universe. The observable universe is defined by a specific physical limit. It contains only the regions from which light has had enough time to reach us since the Big Bang, approximately 13.8 billion years ago. Light from sources more distant than approximately 46 billion light-years in any direction has not had time to arrive. Those regions exist. The physics of the Big Bang does not stop at the boundary of what we can see, but we cannot observe them, and we cannot reach them, and we cannot know in any direct sense what is out there. The actual universe, the full extent of what exists beyond that observational horizon, is estimated, based on the most conservative applications of standard cosmological models from the Planck Collaboration's 2020 data, to be at least 250 times larger than the observable portion. At minimum, some models suggest it may be effectively infinite. The observable universe, with its 2 trillion galaxies and its 93 billion light-year diameter, is not the universe. It is the universe's thumbnail, the sliver of it that happened to emit light early enough for that light to have traveled far enough to reach one small planet in one unremarkable galaxy, in time for the creatures there to detect it. Humanity is agonizing over 4.24 light-years while sitting inside a universe so vast that traveling at the speed of light for the entire remaining age of the cosmos would not reach its edge if it has one. So the real question, the one that sits underneath every number in this story, every engineering problem, every sacrifice, every generation born and dead on a ship moving through the dark, is not whether we can reach Alpha Centauri. The real question is this: if the universe is so immense that consciousness cannot meaningfully conquer it, if even our most heroic reach barely moves the needle on the scale of what exists, then what is the purpose of existing? What is the meaning of exploring? What justifies reaching toward stars that will always outnumber our capacity to visit them by a ratio so large it cannot be written? Maybe the answer is not arrival. The universe does not care about us. It was not arranged for our convenience. It did not calibrate its scale to match our ambitions. It is not waiting for us to cross it, and it will not notice if we never do. The 2 trillion galaxies and the 400 billion stars and the uncountable planets will continue whether or not a small, fragile species on one of them ever manages to land on the rock orbiting the nearest star. But we care about the universe. That is the extraordinary fact, the asymmetry that has no obvious explanation. A species that evolved to find food and avoid predators on a single African savanna somehow developed the capacity and the compulsion to look up, to measure, to wonder, to reach. Not because survival required it, not because the cost-benefit analysis worked out, because something in the architecture of human consciousness finds the scale of existence not paralyzing, but magnetic. The journey to Alpha Centauri, with all its terror, all its cost, all its near-certain failure modes, all its generations of sacrifice, is not primarily a mission to a destination. It is an expression of what the species is. Every obstacle laid out in this story is real. Every risk is genuine. The physics does not lie, and the engineering does not negotiate, and the universe does not care. And yet, the fact that a species capable of understanding its own smallness still chooses to move toward the stars anyway, that might be the most remarkable thing in the entire observable universe. Not the stars themselves, not the distances, not the physics, the reaching. That we look at 41 trillion kilometers of void and say we are going anyway. Maybe that is the answer. Maybe that has always been the answer. And maybe the universe, indifferent as it is, has never seen anything quite like it before.